Without further ado, I will give the word to our moderator for today's session. Pedro Ribeiro is a PhD student for the Spintronics and Biosensors group. So Pedro, the floor is yours.
So yes, so hello everyone, and welcome to this seminar from organized by INESC MEN. So yes, today we have Ruben Afonso presenting, a PhD student from both INESC MEN and the INESC IDE, and he will be presenting the work electronic platforms for magnetic biochips, about the work that he has been developing so far during the course of his PhD studies. So Ruben, whenever you're ready, you may begin.
Thank you, Pedro, for the nice presentation, the introduction. So I will talk about electronic platforms and signal processing for magnetic biochips, and it will be focused on dynamic detection using magnetic flow cytometry. So classic flow cytometry is a technique used to count, analyze, and classify microscopic particles in a liquid medium. This analysis is performed by suspending one entity, such as a cell or a bacteria, in a stream and passing them through a sensor. These cells can be labeled, for instance, with a fluorescent marker or not, and in this case, we use interference light patterns to detect it. In magnetic flow cytometry, the targets to be detected are previously labeled using supermagnetic bits, and the samples flows through a microfluidic channel with several magnetic sensors. Being paramagnetic, external magnetic field is needed to magnetize the particles, so a permanent magnet is used to generate a external magnetic field B. When these entities pass over the sensor, a variation in the magnetic field is generated. So a variation in the sensor resistors is detected and amplified, and we have a sensor with this shape. This technique can be used to detect several targets, but in our application, we want to detect bacteria. However, one of the biggest problems with this kind of systems is to distinguish between labeled cells or labeled bacteria and agglomerates, since both can have pulse with similar shape, duration, and amplitude. So our goal is to create a compact system capable of autonomously analyzing a biological sample. The system must identify several types of particles, count only labeled entities, and of course should be portable. This work use sensors designed by Rita Soares from INESC MEN that we can see in this picture that have several microfluidic channels, and each microfluidic channel have at least 7 high sensitivity magnetic sensors with a nominal resistance around 500 ohms. The distance between each sensors varies in order to have different detection times, and we can have different patterns on the output signal. For example, if you have 2 sensors, space X, depending on the flow rate, a signal will appear first on the sensor 1 in blue, and second, and moments later, on the second sensor on the orange one. Since the particle can go at different heights, also the voltage can also vary. So, knowing the flow rate, we can calculate the average linear velocity inside of the channel, calculate the time that the particle is on top of the sensor, and calculate the minimum frequency needed to capture these events. In our application, we need a flow rate of 10 micrometers per minute, so we need a minimum frequency of 83 kilohertz. But how can we are able to read the sensors? In literature, several approaches are used, but mostly use very simple bias schemes like a full Wheaton bridge or half bridge, or also high-end current supplies, current sources. Wheaton bridge topology have several advantages, mainly compensate for external error source, such as voltage and temperature. However, using multiple sensors inside of the channel could cause signal cancellation if multiple particles were passing through the several sensors. Also, half Wheaton bridge requires compensation and tuning the resistors and is less sensitive. On the other hand, the current sources are independent, can independent measure each sensor, and also did not depend of the external voltage. In our work, we decide to have discrete current sources. A voltage reference is used, a precision voltage reference is used at the input of this amplifier that generates a voltage across R3. Since it's the amplifier, the voltage in R3 is the same on VREF, but we force a current in R3. The current on R3 is the same on Q2 and is the same on Q3. So, since the base voltage of Q3 are the same as Q1, the sensor will have the same current that we have on R3. So the sensor have the same current as the current reference. This architecture is independent from the sensor resistance value and is easily scalable. To add a new sensor, we just need to add one more PNP transistor and a resistor. In relation to signal amplification, assuming that the maximum voltage that we can acquire is 250 microvolts plus or minus, we need again around 20,000 with a bandwidth of 100 kilohertz to acquire all of these signals. So it is very difficult to have an amplifier with these specs. The solution is to cascade gains to have a high-end gain and increase the bandwidth of the whole system. However, these have a cost. More noise, we add more noise to the output, and also we have higher offset at the end. We can also verify that each stage had a noise proportional to its gain. So most of the output noise is driven from the first stage. This means that if we can, we must have the greatest possible gain on the first stage. Since we have a fixed gain bandwidth product, we cannot change the gain without changing the maximum bandwidth of the amplifier. So we need to make a trade-off to select the best gain and the best to accommodate this bandwidth. In our case, we have two stages that use amplifiers from analog device with a very low noise spectral density. In short, each electronic channel developed has a similar architecture to this. We have a current source from 100 nanoamperes to 10 milliamperes, directly biasing a spin valve, a high-pass filter to remove the DC component, two amplification stages, the first one with 1000 and the second one with 30 to have a total gain of 90 dBs. And finally, a low-pass anti-aliasing filter at the system bandwidth. With this approach, we can have a maximum flow rate of 10 microliters per minute, and we managed to reach the required system bandwidth with only 2 stages. The integrated noise in this bandwidth is 7 microvolts RMS or 19 volts peak to peak. To achieve this acquisition, I started by designing and manufacturing a PCB for magnetic signal acquisition that we can see on the you can see on the right. The board is divided into channels. The left one is the channel 0, and the right is the channel 1. At the bottom, we have the current drive circuitry, which allows us to select one of the possible 3 configurations: a current source with mirrors that I previously talked about, a current source with direct feedback. So the feedback is not on the first resistance, is the one sensor is the feedback, and also half Wheaton bridge. The amplification circuitry is on the top, and with the current configuration, we only can read each sensor single-handed. Connectors are also used to allow a future expansion of this board using external models. During design, the current loops were also minimized using only 2 planes for the power distribution that we can see on this image and the ground plane. As you can see in the picture, assuming that the battery is connected here, the current can only flow inside of each model, inside and outside of each model through these gaps. So we are making in this point a star grounding scheme. This scheme prevents noise induced from one model to coupled with to another. This is extremely important since we are dealing with low voltage signals at the input. We also have built-in self-test mechanisms, such as magnetic field generator at the bottom, warning overload warning on the top, and voltage monitoring to see when the board is working and when it stopped working. So, also on the PCB sensors, we have a self-test coil printed on the PCB, and these are used to generate a magnetic field to test if the magnetic sensor is working properly or not. Also, we can have shields to avoid electromagnetic interference. The typical setup that we use on the magnetic flow cytometry is this. We have a syringe pump to set the flow rate, our platform in the middle, and at the end we have a signal commercial of the shelf ADC converters to acquire the analog signals and pass it through a computer. Once the data is, however, this data is stored in raw CSV files, and we have a throughput of 14.7 megabytes per second. Since each experiment takes around 20 minutes, at least 16 gigabytes of data is generated and must be stored. Then, when we need to load this data, it took almost 20 minutes to load the memory with that. So we need to find a solution. Our approach was to change the data type and store it in Python binary format to decrease its size and to maximize its loading time, to minimize its loading time. So we start by loading the CSV file, import it to Python using pandas, add information related to the experiments, such as software version, hardware version, the channels used, when, the chip ID, and so on. Add this metadata in a dictionary and save it in a file with a quarter of the size. Also, this file can be loaded in around 10 seconds. So a huge improvement in performance. Since we are talking about data structure, each event that we detect is also stored in its own format. Imagine in case that we have a sparse signal and lots of noise. This event in the middle is the important. So when we find it, we only save these events and around it. We do not save everything. Later, when we analyze and we detect that we have two peaks, we create another structure that have all the characteristics of each peak, such as minimum voltage, maximum voltage, time peak to peak, and so on. Regarding the data flow, most of the current systems have a mechanism similar to this. We have the acquisition system. After the acquisition, the data is fed through an automatic event detection, and the number of events are exported. Our approach divides the data processing in several steps. First, we calculate a baseline with water or with the buffer solution, and we use this value. Second, we set a value 2 to 3 times higher and find everything outside of these values. Also, after that, we find all the peaks, maximums, and minimums outside of the baseline. And finally, since we know the velocity and we can estimate the time it takes to travel between the two sensors, we can match the signals from the two sensors. However, most of the times, sometimes the algorithm detects something that is just noise. For instance, the algorithm detects the second waveform as a valid peak, but is not. So we add a validation step to our algorithm to perform a manual verification of each event. A graphical user interface was developed to aid this task and shows only the events found one by one, and the user can change the markers, see the values, and it must select if it is a valid peak or not. After that, export can be made to MATLAB or to other spreadsheets with all this information. To see the performance of this algorithm, we analyze 40 samples, 33 from hospital samples, positive and negative, 3 controls, and 7 controls. Most algorithms in literature use a simple threshold of 3 times the standard deviation of the signal, so the 3 sigmas. This value is selected since 3 sigmas, using 3 signals, 99.7% of the noise will be inside of these values, since the noise have a normal distribution. So if you use 3 sigma, we detect 1000, and if you detect 5 sigmas, we only detect 400. However, since we have this algorithm, we can reduce the standard deviation use, and now we are using 2.3 sigmas, and we detect 10,810 events. So after the proposed algorithm, after we manually validate each peak, from this 10,000, only 1,695 of these events are valid. We consider valid. So we detect only 25 compared with the 3 sigma threshold and the 5 sigma threshold. We only detect 21% and 7% respectively. So we have an improvement in the detection of 67%. The last step is considering the microfluidic and magnetic simulations from bacteria. We know the bacteria, to be a bacteria, the signal must have a time from peak to peak maximum of 81 microseconds and a minimum voltage of 40 microvolts. So using these constraints in our valid events, we can say that we detect 826 labeled bacteria. The next step is to be sure and to see what entity is passing over the sensor and to check if it is really a labeled bacteria. To do so, we use a high-speed camera. This camera can take up to 960 frames per second. So we can only use 2 microliters per minute. But we think it is enough to create a database and start a validation process to classify each of these events. With that, we can have a reliable magnetic flow cytometer. Thank you. Thank you for your attention, and thank you to my team, and thank you to my supervisors. Thank you.
Okay, so thank you, Ruben, for your presentation, for a nice presentation. So does the audience have any questions for Ruben?
Yes, I have one.
Okay, go ahead.
Thank you, Ruben, for your presentation. It was very clear and with a lot of information behind these slides, I guess, and work. So my question here is about this manual validation step. Is it possible in a near future to implement it automatically to avoid this manual process that I suppose it's very time consuming?
Yes, it's
when you show, yeah, when you showed in the algorithm that you have, yeah, a manual verification.
The manual verification. Of course, the objective is to make this autonomous system. So no, we don't want to include always manual validation. Also, you are right. The manual validation is now the time-consuming part. So we have several events, and we need to classify each one. So we are in the near future, we think that with neural networks we can reduce we can improve the detection, and of course this will be an totally automatic validation. So we fed through these events to a neural network machine, and they just say yes, is an event, or not, is not.
Okay. Another thing that I would like to discuss with you, it's about this 2.3 sigma, 3 or 5 sigma.
Okay.
So I don't know if I understood well. When you apply the 2.3 sigma, you end up with about 16% of the peaks validated after manual validation, right?
Yes.
After manual validation. The peaks that are considered to go ahead, then you validate them and you end up with 16%. But when you apply the 3 sigma and the 5 sigma, you end up with about 65% of peaks validated, right? Or not? The 3 sigma, 67%, is that correct?
From the 3 sigma, the 3 sigma and the 5 sigma are all validated. So these events are correct.
Where I where I would like to go with this is that you start in the 2.3 sigma, you start with 10,000, about 10,000, and you extract 1,000, about 1,000 peaks out of this 10,000. When you apply directly the 3 sigma, you don't need to manual validate it.
No.
Because they are all correct. And you also end up more or less with the same number of peaks.
No.
Validated.
No. For instance, if we use the 3 sigma, we have 1,000. And if you use the 2.3 sigma, we have 1,000.
About 600 more. Okay.
So it's 67% more.
No, my question here is if it was more convenient to apply the 3 sigma and rely on all the peaks that are achieved, or if this manual validation is worthwhile doing it, and this is a compromise, or we lose some peaks with the 3 sigma, or
I can also give another insight. If we want to have a neural network, we need to have good examples and bad examples to train the network. So this manual validation is really important to, in the future, we have both sets, and to the neural network can do a similar job that the human do. Okay.
Okay.
So yes, we can rely only on 3 sigma, of course, but now we will lose some data and some events.
Thank you.
So, okay, so Diogo, you can go ahead and ask your questions.
Thank you, Ruben, for your excellent presentation. So, coming after this question from Veronica, so you are already saving a database with all these validated pulses and validated as non-pulses in your for future reference.
Yes,
that's actually very arduous work that has to be done.
Yes, and also this is for that reason that we only save this portion of the signal. We can replicate everything outside of this because it's for now it's just noise. But if we save that part, we can feed this information to the neural networks. And since we have the classification state, if it is valid or not, we have our first data set ready. What was the question? Sorry.
Yeah, I was just asking if you were building the data sets already. Yeah. So now, from these examples, you already have 10,000 examples of non-validated, non-true pulses and 1,600.
Yes, we have more. Yeah, we have more, but these were from a context to test hospital samples. But we have sparse information, some controls, some positives that are not linked together, but this number increase. So we have around double that information.
Okay. So okay. So if there are no more questions, I have a question for Ruben. So on your slide 24, where you were speaking about the baseline, you referenced that you have to take a measurement of the base. So how often do you have to take a measurement of the baseline every time you want to do your test, or is the baseline always more or less the same? So do you always take a measurement of does the baseline change a lot between measurements? That's my question.
No, if we measure every time, yes. Okay.
So okay, so what do you mean exactly if you measure every time?
Okay, so we don't, in reality, we don't need to make the baseline. Okay, we can just integrate the signal, a small part of the signal, that at the beginning of each experiment, and it must be noise. So, and we can use that value as the baseline. However, since we are testing the device each day that we need to make some experiments, in the beginning we will pass through a buffer solution or water just to have a file that day to, for instance, we have a couple of problems that we have some interference, magnetic interference, and we just use some water to test that and say, okay, we cannot test it here, we cannot test this today, so just stop it. Okay, so this is also one problem.
Yeah, just to add here that when you mean magnetic interference is when you reuse the chip. If you have a reused chip that already has particles from previous experiments, if it was not well washed out, it can have some particles that interfere in the next experiment. Is that, I guess that
No.
Ruben, no, Ruben?
No.
Okay, so clarify,
this,
sorry.
No, if we have some particles remaining, of course, the end result, so the number of bacteria or cells counted will be affected, of course, but the interference that I was talking about is not that. For instance, I was talking about the motor of the fridge start and generate a lot of magnetic noise, and we cannot use the system on its side, for instance. Because for the electronics, if the sensor have more particles that should not be there, it cannot affect the sensors. It will affect the results, but will not affect the electronics because they will detect.
Okay, thank you, Ruben. Deborah, you can go ahead.
Hi, Ruben, great talk. I just want to have a small question. So have you started doing the analysis of the data already with the neural networks? And if so, what type of neural networks are you using? Convolutional neural networks or?
No.
No, you haven't started?
No, I haven't started. Stop.
Okay. And have you thought about what to use?
Yes. Also, in our team, we have a person, Diogo, that already makes some neural networks to be used in this case. But personally, I don't start any neural networks, or I don't know which kind of neural network should I use.
Okay. Okay, thank you.
Sorry.
Diogo, you can go ahead. You are muted, Diogo.
Sorry, I have a question, but first I can answer Deborah a little bit. So I have used feed-forward neural networks, simple feed-forward neural networks with one to three layers, and it gives exceptional results. Maybe using convolutional neural networks could be an idea, but they are complex and probably they will be useful for the next step Ruben is working on for the imaging processing. But for the signal processing, this type of signal, the feed-forward will probably be enough. But I had a question for Ruben regarding this baseline. Do you think, since one of the problems is the size of the data, do you think that by knowing the baseline and applying some kind of threshold or something, it could also reduce the size of the data because everything else is irrelevant? I don't know if this makes sense to you.
So you are saying so just save things outside of the baseline?
Yeah, basically that.
Yeah, but bipolar pulse passes through the baseline.
Oh, yeah. Yeah.
So
I was saying just save the chunks of data where that occurs. So
yeah, but to do so, we need to have we must have a 3 sigma or 5 sigma or some kind of this, because if we try to because if I don't know, if we have double, we can reduce the baseline. Okay, we don't save anything on the baseline unless they have some sort of trigger outside of this value. Okay, but after that we need to save when it started, its duration, and so on. So if we have noise, if we inside of that, we will just increase its complexity to save it, and I think it's not worth it.
Okay. Yeah, I also think that, but since you've been working with it so much and trying to reduce the data size, maybe you have a difference.
Yeah. Also, the data can be compressed even further, since they are around the same noise value. But for now, we're just trying to have easily accessible files and formats to use. So
yeah.
It's
better this for everyone else. Yeah, also is using.
It could be and will be a the final steps if you have, for instance, a point of care device that we don't care about the noise, the baseline, but we only save the events. But for now, we want to have the most data possible, so we will continue to save it.
Vanya?
Yeah, thank you for the nice talk. I wanted to ask you, because you are working with this in this project for quite some time now, what do you think this system still needs to be truly robust in an electronics point of view?
In the electronics, I also considered the detection, not the detection, the final validation. Yes. Yeah. Okay. So in my point of view, this is the final step. So because if in the previous experiments we could, for instance, have a concentration, so we put you have 10,000 and we detect X, and if we put half, we detect X half too. So if we could have this correlation, maybe we don't need this tool. But since we don't know, and sometimes we have too much, we have more detected events than we are thinking about. So we really need a tool or a database to check what is that magnetic signal. So, and the best way for us is to see the particle or the interaction between the magnetic particles and the sensor, and create a database to say, okay, if you detect this type of event, is X. If you detect these are just agglomerates, or there is nothing, and so on. So for me, this is the very, very important step to make a reliable system that people can trust. And I think people outside of the the research community can trust. So to have a doctor or analytic to use the device and say, okay, I can trust this.
So, okay, go ahead, Vania.
Okay, you are mentioning the trust. I was mentioning more like for the robustness of the whole system. Like either you think it's necessary to, I don't know, increase the frequency of acquisition, or you think that, for example, that would work very well with lower power than it is working now, or like, do you have some idea that could contribute to the development even further for this technology to become more and more robust?
Yes, increase the frequency increase the frequency will be the best step to have more, to accommodate more flow rate. So we can, and using higher flow rates, some problems with the microfluidic channels also do not apply. So for instance, sometimes since the particles are slow, we make a jam inside of the microfluidic channel. But if we use higher flow rate, we can use more sample, so more diluted sample, for instance, and this can increase the performance and also the reliability. Also, the interaction between the mechanical aspect of the system also need to be addressed, because now we are just using tubing inside and in the inlets and the outlets, and we must have some sort of sample preparation and so on in the chip, that we don't rely on external steps. And finally, I was thinking about sorry, I forget. It was something that you said about, it was the frequency and
I said I was talking about the power, for example, to include strategies that would enable to work in lower resources or something like that.
Yes, yeah. We are using batteries. We need to use batteries to power the device, since they have low noise. So of course the system could be miniaturized and have a box with everything to be using in less development countries or in the field without need a power outlet and so on. But to achieve that, we also need to achieve the point when we say that if it is a valid or not, to at the end we have a device that just say yes, no, yes or no, or we have detected X amount with a probability of X. So we also need to put every signal processing and the algorithms, or if you use neural networks, we need to put everything this in the embedded system and put this on a box, and that will make a point of care device. But the power consumption of the magnetic acquisition and driving for now is not an issue.
So yeah, last call for questions. So if there are no more questions, I would like to thank Ruben for his great presentation again, and also the audience for being here. I don't know, Vani, if there are some sneak preview details for the next seminar.
Too many buttons at the same time. Well, thank you so much, Ruben. Thank you, Pedro, for the moderation, and all of you for asking questions and making Ruben think a bit more on the work he is developing. So before we leave, I wanted to remind you that our next INESC seminar will be on July 9th. And it will be given by Dr. Emilio Nogales. He is associate professor at the Universidad Complutense de Madrid in Spain. And it will be on beta gallium oxide nano and microwires for widely tunable optical microcavities. So thank you so much to you all, and have a great weekend.